Anybody having syllabus with you?
Yes, sir.
Okay, so unit 1 we completed already. So unit 2 is mainly for pharmacokinetics and okay, one second. See, second unit we completed, right? Except this calculation part. Is my screen visible?
Yes, sir.
Yeah, can you check? I think almost completed the second unit, right? Except this pharmaceutical calculation and kinetic model. Somebody can respond.
Yes, sir.
Yeah, okay. So now I just moved to the third unit, right? So maybe some other another day we will have the calculation part, numerical, right? So I may need 1 or 2 hours. So we'll solve some 20-25 problems related to pharmacokinetics, right? So today I just wanted to start the third unit, which is pharmacodynamics. Okay. So yeah. So in pharmacology, so we mainly study about 2 things. One is the pharmacokinetics, and another one is the pharmacodynamics. See, one more thing is that so when is the next class? Tomorrow do you have class?
Wednesday, sir.
Wednesday, right? So Wednesday you will be having the quiz, okay? Because they asked to finish all the quizzes end of this month, right? So I think we have to finish at least 2 quizzes immediately, okay?
Okay, sir.
So Wednesday you'll be having the another quiz. The syllabus for the quiz is the first half of second unit. Again, I repeat, the syllabus for the next quiz on Wednesday is first half of the second unit, pharmacokinetics. Okay, right? So we mainly we study about pharmacokinetics and pharmacodynamics under the pharmacology. Pharmacokinetics is like various parameters like absorption, distribution, metabolism, excretion. So these are the various parameters which are studied under pharmacokinetics. So meaning what the body does for the drug molecule. In simple words, that's called as the pharmacokinetics, right? So what is meant by pharmacodynamics? What the drug does for the body? What the drug does for the body. Okay, simple way to define what is meant by pharmacodynamics. So mainly what we study under pharmacodynamics is like how the drug molecule goes and bind to the drug target, and how it makes the complex formation, and how that complex formation lead for the biological response. So these are the things which are studied under pharmacodynamics. Okay, so that is what I have illustrated in this slide. So we have the drug molecule, right? So once if you take the drug molecule, once if you intake the drug molecule, once if the drug molecule enters into the body, okay, so several events are taking place. Certain events comes under pharmacodynamics, and certain events comes under pharmacokinetics, right? So as I said, pharmacodynamics is what the drug does for the body, and pharmacokinetics is what the body does for the drug molecule. An example for pharmacokinetics is metabolism. So once if you take the drug molecule, it reaches the liver, where maximum amount of the drug molecule will get metabolized, right? So example for pharmacokinetics, so if you have fever or if you have body pain, so if you take some drug molecule, so after some time we may expect that there will be kind of reduction in the fever, or whatever purpose for which the drug molecule is taken, right? That is called as the drug action. So two terms, you should not get confused. One is called as a drug action, another one is called as a drug effect, right? Sometimes it may confuse. We'll see what's the exact difference between the drug action and drug effect, right? So the meaning of drug action is how the drug work, right? So normally, if you take any drug molecule, FDA approved drug molecule, if you ask a question, how does that how the drug molecule works, right? So it goes and bind to the corresponding drug target. So cells will be having some drug target to which the drug molecule should go and bind. So after binding to the drug target, what actually happens is that either the drug molecule will activate that receptor protein molecule, or it can inhibit. It can activate or it can inhibit the protein molecule, right? So that is how the drug action is taking place. So what's the meaning of drug effect? The meaning of drug effect is, so consequence of drug action. So because of the binding of the drug molecule, because of the activation of the protein, or because of the inhibition of the protein molecule, what happens is some effect will takes place. That is what exactly is called as drug action on body. So example, aspirin, a very commonly sold drug molecule. So if you take aspirin, so the action, biological action of aspirin is it block a protein which is responsible for synthesizing a prostaglandin. Okay, so it goes and bind to the protein that synthesizes prostaglandin. So the effect of aspirin is because of the inhibition of the protein which synthesizes prostaglandin. So this molecule produces the biological effect called as analgesia or antipyresis. It reduces the fever, or it reduces the pain. Okay, all this are called as the drug effect. Okay, so this is what I illustrated in my previous slide. The way by which the drug act is like the drug molecule will go and either bind to receptor where it activate or inhibit the receptor, or it can go and bind to some ion channels. The many ion channels which are present in the cell, it can go and activate or inhibit the ion channel. So many enzymes which are present, again it can activate the enzyme by binding to it or inhibit the enzyme. Many carrier molecules, okay, so it can activate the functioning of the carrier molecule, or it can inhibit the functioning of the carrier molecules, right? There are some expectations, right? So not necessarily that all the molecules should act in this same way. There are some expectations. There are many antibiotics, anti-cancer drug molecules. Their mode of action may be completely different, right? So anti-cancer drug molecules, they may go and bind to DNA, okay, where it can inhibit the synthesis of DNA. Antibiotics, it can kill the bacteria. The mode of action of those molecules may be slightly different, not by activating or inhibiting some protein molecules which are present in the cell. Okay. So the mode of drug receptor binding is like, say this is the enzyme. This you might study in your biochemistry in very detail, right? So each protein molecule will be having some binding cavity. We call it as an active site or binding site, to which the substrate molecule will go and bind. And this is very selective. Not all the drug molecules can go and bind to all the protein molecules. So there are two types of complementary is needed. One is called as shape complementary, and another one is called as stereoelectronic complementary. So if any substrate or the drug molecule that has the shape complementary and stereoelectronic complementary, then they can go and bind to the binding site of the protein molecule, where it can make interaction with the active site to form this complex, right? So this complex is mainly responsible for the biological response. Okay, the drug action is mainly because of the formation of this complex that we will see in detail in the coming slides. Okay. Okay, so now our understanding is that most of the drug molecules, it will be having some drug target molecule to which the drug molecule should go and bind. Okay, so for most of the drug molecule, right? So there will be corresponding drug target to which the molecule should go and bind. That's our knowledge, right? So we say that the drug molecule, after the binding of the drug molecule, it forms the complex and that lead for biological response. Okay, so there are so many theories that explains how this the drug response is taking place. Okay, so what's the reason for the drug response? Okay, so there are so many theories which are proposed. So these are the common very important theories that explains the pharmacodynamics of any drug molecule. First theory is called as Clark occupancy theory. Second theory is Arrhenius theory. Third theory is Stephenson theory. Fourth theory is the rate theory. And the fifth theory is the two-state model theory. And these are the various theories that explains the actual relationship between the drug molecule and the drug target. Okay, that is what we are going to study, right? So literally what we are going to what I'm going to teach you is that how this drug molecule goes and bind, and how the binding of this drug molecule to the target site lead for the biological response. Okay, all this theory explain how that process is taking place, right? So let me start with the very first theory called as a Clark occupancy theory. Okay, so Clark is a name of scientist who first came up with an idea, proposed idea to explain how the biological response is taking place because of binding of drug molecule to the drug target. So he made some hypothesis. He started like he made some basic assumption to develop this theory. And the first assumption what he made was like, so the drug molecule that binds to the receptor, where it forms the drug receptor complex, and this drug receptor complex is responsible for the biological response. So this is a simple concept, right? So many times I repeated. So drug bind to the receptor, where it forms a complex, drug receptor complex, and which lead for eventually the biological response, right? So he made some assumption to explain what actually happened inside the cell. So he called this as it's a biomolecular dynamic equilibrium. So this equilibrium, he called it as it is a biomolecular dynamic equilibrium, which means that the reaction can either takes place in the forward direction or it can takes place in the reverse direction. Okay, so both are possible. Sorry. Yes. So this reaction is a biomolecular dynamic equilibrium reaction. So there exists a forward reaction, also the backward reaction, which means that this complex formation is not permanent, it's temporary. So after some time, the drug molecule will be released from the complex, and the drug and the receptor molecule will be dissociated back, right? So both the reaction will take place in both the direction. That is his first kind of hypothesis or first assumption what he made. It's a biomolecular, there's a biomolecular dynamic equilibrium. So the second assumption what he made is like the intensity of the response, right? So here the intensity is say for example, if we plot a graph between response, okay, and the dose. Okay, so say for example, if we increase the dose, so this is the way by which the dose increases. So if we increase the dose, what we may expect is that the response may get increased, right? So if we increase the concentration of the drug molecule, we can expect the response will get increased, right? So what is the response here? So for example, it may be reducing the fever, whatever it is, right? So whatever purpose for which the drug molecule is taken, that is the response. So if I take minimum quantity of the drug molecule, I can expect minimum amount of the response. If I take more quantity of the drug molecule, I can expect more amount of the response, right? That is what is called as intensity. So this is the intensity. of the response, right? So the intensity of the response at any time was proportional to the number of receptors occupied by the drug molecule. Say for example, if you have a cell and you designed a drug molecule for targeting this protein is the drug target which is present inside the cell, for which you have designed the drug molecule, and this is your drug molecule, right? So if only one drug molecule binds to the receptor, we can expect some quantity of the response. If two receptors are occupied by the drug molecule, we can expect more amount of response, right? So if half of the receptors which are present inside the cell, if all are occupied, then we can expect more amount of response. So if all the receptors which are present in the cell are occupied by the drug molecule, we can expect more amount of response, right? So the intensity of the response now, it depends on, okay, the number of receptors which are occupied by the drug molecule. Is it understandable?
Sir.
Yes, right? Okay. See, if you have any doubt, you can stop me, right? So here we can formulate the expression like the response effect E, okay, is directly proportional to dr, okay, which means that the effect which is proportional to the number of receptors which are occupied by the drug molecule. So if we write something like this, which means that the concentration of the drug receptor complex, concentration of drug receptor complex, okay. um, so that is the second assumption what he made. The third assumption is maximum response. When we can expect maximum response? So we can expect maximum response when all the receptors are occupied with the ligand molecule. That is what I illustrated here. So if you have say 100 receptor in the cell, and if all the 100 receptors are occupied with the drug molecule, then we can expect the maximum response. Is it understandable? So the maximum response effect Emax given by Emax is directly proportional to RT, where RT is the total number of receptors within the cell. Is it understandable?
Yes, sir.
Yes. Okay. So E by Emax is called as a fraction of maximum response. In the previous two slides, I have explained what is E, what is Emax. E is the response effect, and Emax is the maximum response effect. Okay, so fraction of maximum response is calculated by E by Emax. So E over Emax, that is equal to dr by dt. Is it understandable? Dr by RT. Is it understandable?
Yes, sir.
So fraction of maximum response is a dr over RT. Okay, so E by Emax is the fraction of maximum response we can expect at the given time. Okay, so this is very simple derivation. You might study the same in your 10th or 11th standard, right? So simple expressions, right? So again, I am taking the same equation, drug molecule that binds to the receptor, okay, where it forms the drug receptor complex, and that formation of drug receptor complex will lead for the biological response. So Kd is the equilibrium constant for this reaction. So because this reaction is going in both forward direction as well as in the reverse direction, so there should be some equilibrium constant Kd. So the Kd value is going to decide whether the reaction is going faster in the forward direction or it's going faster in the reverse direction. That's given by Kd. So Kd is equal to D, concentration of the drug molecule, times concentration of the receptor over concentration of the drug receptor complex. Okay, it's very simple. So Kd is the concentration of the drug molecule, concentration of the receptor over concentration of the drug receptor complex. Is it understandable? This is the equilibrium constant expression for the given reaction. Is it understandable?
Yes, sir.
Yes, right. So now we can write the equation expression like Kd is equal to slight rearrangement, right? So we are not doing anything. So Kd is equal to concentration of the drug molecule. Okay, so here we know that what is this? Uh, okay, so yeah. Uh, what is R? One second. Kd is equal to concentration of the drug molecule times uh, okay, so the total receptor concentration here is RT. Total receptor concentration is equal to RT is equal to the total number of receptor plus the total number of drug receptor complex. Is this expression understandable? Total number of receptor is equal to free receptor plus the receptors which are complexed with the drug molecule. Okay, if you don't understand, say for example, if we have these are the receptors. Okay, so these are the receptors which are occupied already by the drug molecule. So how to calculate the total receptor? The total receptor is the number of free receptor. So in this example, the number of free receptors are 2 receptor plus the number of receptors which are occupied by the drug molecule, which is number of free receptors are 3, and the number of receptors which are occupied by the drug molecule is 3. The total receptor is 6. Is it understandable?
Yes, sir.
Yes, right. So now in this equation expression we have R. Okay, so we can rewrite this like R is equal to, okay, so R is equal to RT minus dr. Is this expression right? And just rewriting R is equal to, I have to push this here, right? RT minus dr. Is it right?
Yes, sir.
So if we substitute that at this R position in this equation, okay, so what will happen? We will get this expression Kd is equal to concentration of the drug times RT minus dr over dr. Is this expression understandable?
Yes, sir.
Yes, right. So now from this point everything is just slight rearrangement of the things. Kd is equal to we can rewrite this expression as d concentration of drug times RT by dr minus concentration of the drug times concentration of drug receptor complex over concentration of drug receptor complex. Is this expression understandable? Just a rearrangement of the equation 1. Is it
Yes,
understandable?
sir.
So from this we can derive the third expression. Just again, rearrangement and cancellation. Is it understandable? So dr is cancelled here.
Yes, sir.
So we will get minus d. So we can rearrange this again like kd plus, just bring this d to the left hand side. So kd plus d is equal to d concentration of the drug times concentration of RT by dr. Is this expression understandable? Fourth?
Yes, sir.
Yes, right. Okay, so again we can rewrite this to the fifth expression kd plus d by d. This d is now from the numerator to denominator, right? So is equal to RT by dr. Is it understandable?
Yes, sir.
So now here we know that fraction of maximum response, in the basic assumption we said that E by E max is equal to dr by RT. So here we have the value, here we have the expression which is having dr by dt. So if we substitute this to this dr by dt, we can say that E by E max is equal to dr by dt, dr by RT is equal to concentration of the drug molecule by Kd plus concentration of the drug molecule. Is this expression understandable? This is a very last expression. Is it understandable?
Yes, sir.
Yes, this equation is called as Clark equation. Very important equation that explains the relationship between drug molecule and how it binds the drug target to produce the biological response. So this E by E max is equal to dr over RT is equal to concentration of the drug molecule by Kd plus concentration of the drug molecule. So have you ever seen this type of equation in your biochemistry, if you remember? Hmm? Any equation have you studied something similar to this equation? You can very easily remember. I'm looking for kind of response. So have you studied kinetics, enzyme kinetics?
Yes, sir.
So in which you might study about Michaels-Menten equation, right?
Yes, sir.
Okay, this equation is very similar to Michaels-Menten equation. So what is Km in Michaels-Menten equation? It's Michael's constant, right? What's the significance of the Km? What is the significance of Km, Michael's constant in the kinetics, enzyme kinetics? If you know, you can respond. If you don't know, you can tell you don't know. See, Michaels-Menten. So we have to plot velocity versus concentration. Okay, what's the meaning of Km in Michaels-Menten equation? What does it mean?
Enzyme affinity, sir.
Hmm?
Enzyme
Enzyme
affinity.
affinity? No. What is Km? The concentration. Say if I say this is the Km value, what does it mean? It means that that is the concentration that is required to produce a half maximal velocity. Am I right?
ப்ரிப்பேர் பண்ண வேண்டாம் உங்களோட ஒர்க்குக்கு நான் வந்து ஐ ரிவைஸ் லிட்டில் பிட் ஆஃப் நான் ரிவைஸ் பண்ணிட்டு வந்திருக்கிறேன் ஸோ நீங்க டிஸ்கஷன் எப்பமா நான்
Yes, sir.
இருந்து வந்தீங்கன்னா
Okay, I don't want to go in detail, right? So I assume that you can understand. Again, if you want, I can tell that Km in the Michaels-Menten constant is the concentration. We have concentration on x-axis and velocity on y-axis. So what is the concentration that is required to produce the half maximal velocity? Okay, so exactly 50% of velocity, right? So that is what is called as a Km. So here the Kd is called as it's called as it is also constant. Okay, so which means that this Kd is called as the concentration that is required to produce a half maximal biological response. Okay, again I repeat, this Kd is the concentration of the drug molecule that is required to produce the half maximal biological response, right? So here, what he did is he made a plot, right? So between the concentration of the drug molecule on the x-axis and the biological response, okay, Emax on the y-axis. So while plotting, what you will get is you will get a plot like this. Okay, so if you do the same thing for log of concentration of the drug molecule versus the response, then you will get some plot like this sigmoidal. Again I repeat, so here there is no log, right? So directly the concentration of the drug molecule versus the biological response, he got a curve like this, right? So I think this is a parabolic curve. So once if we take log for the concentration and he plot the log of concentration of the drug molecule versus the biological response Emax, he got a curve like sigmoidal curve. Is it understandable?
Yes, sir.
Yes, right. So so in this we can easily calculate the Km value. Km is the slope, right? So not Km, Kd is the slope of this, right? So here this Kd we can easily calculate from this. It's the slope, right? So Km in Michaels-Menten equation is the slope. So if we take the slope for this, that will tell what's the concentration of the drug molecule that is required to produce the 50% of the response. So for example, this should be the concentration that is required for 50% of the response. Do you agree? So this should be the Kd value. Am I right? So because we have 100% here, so this is the exact 50% response. So what's the concentration that is required for producing the 50% response? This should be the concentration that is required for producing the 50% of response. Is it understandable?
Yes, sir.
Yes, right. Okay. Uh, yeah, this is a Michaels-Menten graph for enzyme kinetics. So here this is the Km. Here this is plotted between the substrate concentration. S is the substrate concentration and V naught is the velocity, maximum velocity. So Km is, this is the 100% velocity, right? So Km is exactly the 50% here. So Km is half maximum velocity. So maximum, if the maximum velocity is 100, the half maximum velocity is 50, right? So the substrate concentration that is required to produce the half maximum velocity, this Km is called as Michel's constant. So very similar is this Kd, right? So Kd is instead of velocity, right? So instead of substrate, this is the drug concentration on x-axis, and the biological response is on y-axis. So Kd is nothing but the concentration of the drug molecule that is required to produce the 50% of the biological response. Is it understandable?
Yes, sir.
Yeah, that equation is what is called as a Clark equation. So he made some, he hypothesized this everything he based on some kind of assumption what he initially made, right? But all the assumption what he made is not correct. He did some mistakes on making the assumption, because we cannot explain the biological response of all the drug molecules using this. Some drug molecules will not fit. So but if you look at this, we have a good fit here, but unfortunately this fit we cannot expect for all the drug molecules, which means that the assumption what he made, or his theory is having some kind of limitation, right? That's what I'm going to show you, that what are the basic mistake he made in his assumption while developing this hypothesis, right? So the first incorrect assumption is that a formation of many drug molecule may not be reversible, right? This may be new for you, right? So but this is a very interesting thing. So we say that the drug molecule bind to the receptor, and which lead for formation of the drug receptor complex. Okay, and the interaction between the drug molecule and drug receptor is not permanent. So there should be some backward reaction, right? So after some time the drug molecule should come out of the binding site. So that is his first assumption: biomolecular equilibrium exists, but it is not necessary that always there should be a biomolecular equilibrium. So I can give an example for you. Say there is a drug molecule, right? So which bind to the receptor, but the drug molecule is not coming out, right? So it is permanently fitted inside the binding site. Okay, so normally if the reaction has to be reversible, then it should be weak force of attraction between the drug molecule and the drug receptor. Okay, like hydrogen bonding, hydrophobic interaction. But in case, so you had assumed that in case if the drug molecule made covalent bond with the binding pocket of the drug target, covalent bond is a permanent bond. We cannot break it that easily, right? So the drug molecule will not come out easily. It's going to be permanent. Permanently, the function of that receptor is completely inhibited. Okay, so based on that, there are many drug molecules which are approved by FDA. They can form covalent bond interaction with the drug target. Hence, the reaction is not going to be reversible. It's going to be irreversible. Is it understandable?
Yes, sir.
Yes, right. So second basic assumption what he made is wrong is like receptor. According to Clark, the receptor binding site is always independent, right? So what he says that if there is a receptor, its binding site will be always empty, but that is not true. Okay, so maybe some other molecule may be already occupied to this. I just give one example, right? So you can easily understand. So we discussed about there are many protein molecules which are present in the blood plasma. The drug molecule may go and bind to the plasma protein. Okay, which means that the binding pocket of the plasma protein may not be always freely available. Sometimes it may be occupied by some other drug molecule. So in that aspect, we cannot expect that the binding site of the receptor will be always independent. Is it understandable?
Yes, sir.
One more example also I can give, right? So what is the meaning of independent? Say for example, so here we have a binding site. Okay, so here we have some other allosteric site or some site near to the binding site. This is the original binding site. So for the functioning of this drug molecule, obviously this molecule should go and bind to the binding site. There may be some cofactor which may be required for activating the protein molecule that should go and bind to this position. So in this example also we can say that Receptor sites are not always independent. It is dependent. It depends on the cofactor. So without the presence of cofactor, there is no, the drug molecule cannot function. Is it understandable? So for the activation of the drug molecule, what should happen is that the cofactor should first go and bind to that. Is it understandable?
Yes, sir.
Yes, right. So that's what is called as sites are not always independent. The third one is very interesting. We can see very often many protein molecules behave this, will have this behavior. Formation of complex may not be bimolecular. What does it mean? So here, the formation of complex in this example it's a bimolecular. So bi means two. Okay. So the drug molecule bind to the receptor where it forms the drug receptor complex which lead for biological response. So how many molecules are involved in this process? Two molecules. One is the drug molecule and the second molecule is the protein molecule or the receptor. But the formation of complex may not be bimolecular. There are certain protein molecules in which the two molecules of the drug molecule should go and bind for activating the receptor. Okay, so there are drug molecules like that. For the same protein molecule, two molecules should go and bind in two different binding sites. So, for example, if you take acetylcholine, okay, acetylcholine is a neurotransmitter, right? So, which should go and bind to some ion channel, right? So, if you take the ion channel, so two molecules of acetylcholine should go and bind to the ion channel to activate the ion channel. So in this example, we can say that the acetylcholine number of acetylcholine that is required for activating the ion channel is two molecule. It's not one. So for one protein molecule, two molecules of acetylcholine is required. So definitely we cannot say it as a bimolecular reaction. It's a trimolecular reaction. Three molecules are involved in the formation of complex. Is it understandable?
Yes, sir.
Yes, sir.
Yes, right. So the fourth basic assumption what he made is wrong. Is like maximum response according to Clark, right? So what we learned is like the maximum response we can expect if all the receptors are occupied by the drug molecule. Okay, but sometimes maximum response may be obtained even before the receptors are occupied. Okay, so what's the assumption? What's the wrong thing happen here is, so according to Clark, right? So if you have four receptor, so the maximum response we can expect if all the four receptors are occupied with the drug molecule, we can expect the maximum response. But in reality, right? So if you have four receptor inside the cell, just the numbers are just for understanding, right? So don't take it seriously. So if we have two drug molecules only binded to the receptor, two other receptors are free, it's not bind, right? But still there are cases in which we can expect the maximum biological response. I'll give some example for this later, right? So I don't want to confuse you. So this may happen, right? The point is that it is not necessary that for getting the maximum response all the receptors should be occupied by the drug molecule. There are many cases in which even fraction of drug molecule binding to the receptor may lead for producing the maximum biological response. Is it understandable?
Yes, sir.
Yes, right. So I give example later, right? So no need to worry about that point. Okay. Okay, this point is also closely related to the previous one. Response is not linearly related to proportion of receptor occupied, because we have some concepts like partial agonist. In that case, even if all the receptors are occupied by the drug molecule, we cannot expect the maximum biological response. There's 2 points, right? So you just keep in mind, right? So I'll give some good examples later slides. Okay, so these are the assumptions what he made is kind of wrong, because using this theory they were not able to explain the behavior of all the drug molecules. Certain drug molecules fit into this theory, but there are many drug molecules which we cannot fit in this theory, right? So we need some kind of modification or change to explain the behavior of the molecules which are not fit in this theory, right? So in that aspect, the second scientist who came up with a set of ideas to explain what's lack in the Clark occupancy theory. The scientist name is called Arian, and he called it as Arian's theory, right? Second theory is Arian's theory. Very similar to Clark theory, right? So he made very small slight changes in Clark theory, but still he was able to explain, the behavior of some other drug molecule having different characteristic. So this is the first theory which account for agonist, partial agonist, and antagonist, right? So maybe the terms are very new for you. So let me first define what is meant by agonist. So if you have a receptor, and the meaning of agonist molecule is, the agonist molecule is a exogenous molecule that bind to the receptor, where it activates the receptor. Those set of molecules are what are called as agonist. Again repeat, agonist are exogenous molecule that bind to the receptor. It can be exogenous or endogenous, right? So since our drug molecule is exogenous, I am using the term exogenous. The molecule that binds to the receptor and it activates the receptor. Okay, those drug molecules or those molecules are called as agonist. What is a partial agonist? I just use the same image here. So partial agonist that is like a molecule that binds to the receptor. Okay, molecule that binds to the receptor, but it cannot produce the maximum biological response. It can produce only partial biological response. Okay, so for example, so we have two types of, say we have two types of drug molecule. Okay, so both the drug molecules are having the shape complementary with the receptor binding site. So if this, so I name it as A and B. If A binds to the binding site, okay, it is producing the response up to this level. But if B binds to the receptor, it is able to produce only the response up to this. Okay, so then I can say that this is agonist and this is partial agonist. So how do I say that? Because even if I increase the concentration of the drug B, it is not able to increase the intensity of the response. The intensity of the response is very much limited. Are you able to understand that?
Yes, sir.
Yes, sir.
Okay, if you need some more example, you can ask me, right? I assume that you understand. What is antagonist? Antagonist is, say we have another molecule C, which binds to the binding site, but this time, okay, so no response. The line is moving like this. Whatever the concentration I increase, whatever concentration I increase for the drug molecule C, I do not find any response, right? So y-axis is the response, x-axis is the concentration. Even if I increase the concentration, right, I do not find any response, not even small response on the y-axis. Then those molecules we can call it as antagonist. Understandable?
Yes, sir.
Yes, right. Okay, so again coming back to the same story, same thing what he explained. The drug molecules goes and bind to the receptor, where there is a equilibrium exists, where it forms the drug receptor complex, lead for the response, right? So for all the theories we will use the same equation to explain the concept, right? The drug molecule that binds to the receptor, where it forms the drug receptor complex, right? So where the formation of this drug receptor complex lead for the tissue response or biological response. No difference, right? So biological response, both are same thing what he said, Clark, right? So formation of drug receptor complex and the tissue response, right? So he no, according to Clark theory, this takes place in one step, but according to Arian's theory, it takes place in two steps. And also he termed something called as affinity, right? So what's the meaning of affinity? The formation of complex. Okay, the formation of complex that depends on the affinity of the drug molecule to the receptor, right? So let me tell what is meant by affinity. Affinity is the ability of the drug molecule to go and bind to the receptor, right? So not all the drug molecule can go and bind. As I said, it should have shape complementary and stereoelectronic complementary. So once if the drug molecule has a very good shape complementary and stereoelectronic complementary, then we can say that those drug molecules will have higher affinity for that specific receptor. So that is what he termed as affinity. Affinity is the ability of the drug molecule to go and bind to the receptor. So that is the first step, right? So he called this as the first step. So the first step is the formation of drug receptor complex, and that itself depends on the affinity. If the affinity is more, the formation of complex is simple. If the affinity is less, complex may form or it may not form. That's the first step, right? So second step is, so according to Clark theory, right? So I just want to compare all together. According to Clark theory, the formation of drug receptor complex will always lead for the biological response. But according to Arian's theory, the mere formation of drug receptor complex may not lead for the biological response, right? So, which means that not all drug receptor complex can produce the biological response. Sometimes it can produce the biological response. Sometimes it cannot produce the biological response. So the question of interest is when it can produce the biological response, when it cannot produce the biological response, right? So for producing the biological response, this complex should have some inherited characteristic that he termed as intrinsic activity alpha. So he defined this intrinsic activity alpha as the ability of the drug receptor complex to produce the biological response or to initiate the biological response. If the intrinsic activity of the drug receptor complex is more, we can expect that very easily the complex is going to produce the biological response. On the other hand, if the intrinsic activity of the drug receptor complex is very less, very poor, we cannot expect the biological response. Is it understandable?
Yes, sir.
Okay, again I repeat, right? So this reaction takes place in two steps. First step is the formation of complex. The formation of complex, according to Arian's theory, it depends on how much affinity the drug molecule has for the receptor. Okay, that determines the formation of complex. If the affinity is less, no formation of complex. If the affinity is more, formation of complex. That's the first step. Second step is the mere formation of complex may not lead for the biological response. The drug receptor complex should have some intrinsic, inherited characteristic or property that he termed it as intrinsic activity alpha. If the intrinsic activity alpha is higher, then we can expect the biological response. If it is less, then we cannot expect the biological response or tissue response, right? So how to calculate this alpha? So this is a very a new term that is introduced by Arians comparing to the Clark theory. Alpha is equal to Emax of the drug molecule by Emax of the most active agonist in the same structural series. So what is Emax? What is Emax?
Maximum response.
So we are calculating the alpha for this drug molecule. This is our drug molecule. We are calculating alpha for this drug molecule. The formula is Emax of the drug molecule. So Emax of the drug molecule is what is the for this drug molecule? Emax is what's the maximum amount of response we can get for this drug molecule. Okay, again I plot here concentration of the drug molecule versus the biological response. So what I do is that I increase the concentration in this direction. So the biological response goes in this direction. So what we do is we slowly increase the concentration of the drug molecule. So if we slowly increase the concentration of the drug molecule, what should happen? The biological response should get increased. Do you agree?
Yes, sir.
Okay, now at this point the concentration is very high, but I am not able to see more than this amount of the biological response. Some resistance is created here. The intensity is not going beyond this point. What does it mean? Still the concentration is going higher. Not able to see, there is a difference in the intensity. What is your understanding from this? Can we say that this is the maximum response we can get out of this drug molecule? And there is no point of increasing the concentration further. Because if I increase the concentration, I do not find any increase in the intensity. Is it understandable?
Yes, sir.
Or should I repeat? See, these are very... Okay, I repeat, right? Okay. Yeah. Say, for example, we have a drug molecule. we have a drug molecule A and we have a drug molecule B, right? So I am making two plots here. One is for the drug molecule A and the second graph is for the drug molecule B. So this is for A and this is for B. And here we have the concentration on x-axis and concentration on x-axis for this drug, and biological response on y-axis, biological response or tissue response on the y-axis, right? So we know that if we increase the concentration, the biological response we can expect it should get increase, right? So the concentration goes in this direction. So increasing concentration in this direction, goes increasing concentration in this direction. Biological response goes in this direction. So biological response and concentration 0 at this point, right? Say first I am taking some amount, right? So say I am giving 5 mg of the drug molecule, right? So I am checking what's the response, maximum response I got. At 5 mg I got this is the maximum response. So now I double the concentration. I am taking 10 mg of the drug molecule. So I got the response like this. Okay, so I now take 15 mg of the drug molecule. I check what's the response I got. At 15 mg, say there's an increase. At 20 mg, if we check what's the response, 20 mg, we expect that the intensity of the response should go high, but I do not find any change in the intensity. So further, I go for 25 mg of the drug molecule. This time also the intensity is not, increased, right? So can we say this is the maximum biological response we got for this drug molecule? Am I right or wrong?
Yes, sir.
Yes, sir.
Yes, right. So 15 mg, 20 mg, 25 mg, there is no difference. There is a difference in the concentration, but there is no difference in the intensity. Is it understandable?
Sir.
Yes, right. Okay. So coming back to the slide. So Emax of the drug molecule, Emax is the maximum response, right? So in this, can you tell which point is the Emax of this drug molecule? Can we say this point is the Emax of the drug molecule?
Yes, sir.
Yes, right. Okay. So this is the Emax. Emax of the drug molecule. The formula here given by Arians is like we had to calculate the Emax, just what I explained how to calculate the Emax, right? Maximum response that we can get for the given drug molecule is called as the Emax. So next is Emax of the most active agonist molecule in the same structural series, right? So which means that we are not very sure whether our molecule is a agonist molecule or partial agonist, right? So we need some kind of standard molecule. So we have to identify the most active agonist molecule in the same structural series that we are working on, and we have to calculate what's the Emax for that molecule. Say for that molecule, if this is the Emax, right? So this is a Emax for the most active molecule, agonist molecule, that is structurally similar to the molecule which we do the calculation. Maybe slightly confusing, right? So no need to worry about that, right? So everything I'll be explaining in the coming slides, right? So that's a formula for calculating. So E by Emax is equal to if we cut this term, this equation is the same given by Clark. Do you agree? E by Emax is equal to the total concentration of the drug molecule over Kd plus the total concentration of the drug molecule. Am I right?
Yes, sir.
Yes,
The
sir.
only difference what he give in his theory is very simple. He included this term alpha, and he called this alpha as the intrinsic activity. Is it understandable?
Yes, sir.
Right? So we are mainly talking about three types of molecule. One is the agonist molecule, another one is partial agonist, another one is antagonist. Okay. So what will be the biological response we can expect for antagonist? If it is an antagonist, if we plot the concentration versus response curve, what type of curve we will get? Is my question understandable? Somebody can respond.
Yes, sir.
Okay, so again I repeat my question. Yeah. So if I plot a graph between concentration versus biological response, this time I have a molecule which is antagonist. What type of curve I'll get? So in this case, it's a kind of agonist or partial agonist. So what type of curve I'll get in this graph? So for antagonist, will we get any response?
No, sir.
No,
sir.
right? So then what will happen? If you don't get response, so can we say that there won't be any increase in the concentration? We increase, good, but there won't be any response we can find. Am I right?
Yes, sir.
Is it understandable? Then what should be the alpha value for antagonist? If it is an antagonist molecule, what should be the alpha value? Hmm? If it is an antagonist molecule, what should be the alpha value? Because we cannot differentiate whether it is an antagonist or partial agonist or agonist molecule using Clark theory. Okay, so Arians, he advanced the theory using his own concept, intrinsic activity. So my question is, what should be the value for alpha if the molecule is a perfect antagonist? Just now I have shown the graph, no response. Then what should be the value for alpha?
0, sir.
0. The value for alpha should be 0. Is it understandable?
Yes, sir.
Now his theory gives space for saying whether the molecule is an antagonist or not. Are you able to understand?
Yes, sir.
But Clark theory, if you think of that, it failed to explain whether the molecule is. If you do calculation for antagonist using the Clark theory, it won't fit. Am I right? And also we cannot explain the property of antagonist with the help of Clark theory. But by introducing simple one term, alpha, intrinsic activity, now this Arian is able to explain why certain molecules are not showing any activity, because its alpha value is 0. Does it make sense?
Yes, sir.
Yes, right? So if you understand this, the entire story is very simple. So alpha is the new term which is introduced by Arian in his theory. He called it as, a intrinsic activity. So with this intrinsic activity, we can say whether the molecule is behaving like a antagonist molecule or partial agonist or full agonist. If it is a full agonist molecule, the alpha value should be 1. We can expect the maximum biological response, right? So if the alpha value is 0, which means that the molecule is a completely antagonist molecule, we cannot expect any biological response. But in case if the alpha value ranges between 0 to 1, those are the molecules which are acting as partial agonist, which means that those are the molecules which cannot produce the maximum biological response like full agonist. Also, they cannot act like antagonist molecule without showing any activity. The activity will be within the range of antagonist and full agonist. Is it understandable?
Yes, sir.
Yes, right. So this one simple term, he is now able to explain, classify whether the molecule is acting as an agonist molecule or antagonist molecule or partial agonist. Any question up to this I can answer. I don't know whether I went fast, right? I think time is up. Any question I can answer. Okay, so if no question, again I repeat, Wednesday is your next quiz. Okay.
Okay,
Textbook already I have uploaded, right? So I strongly encourage you to follow the textbook. Materials I'll upload it by today, right? So if you want, you can refer, right? So, but don't completely depend on the lecture session or the material which I give, right? So you have to go through the textbook, right? Because the questions what I'm going to ask is completely different, very logic questions, right? So which need more preparation than what I explained in my lecture, right? So you have to do some kind of homework, take some textbook, right? So 2 textbooks given in your syllabus. Take the textbook, just go through completely, right? So whatever content I covered, right? So whatever materials present in the textbook, you should go through. That's the way to prepare for the quiz. Okay. So I think many students did not attend this session, right? So you can inform them also. The next quiz is on Wednesday. Okay. Aishwarya,
Yes, sir.
yeah, you can inform to your class group. Okay, huh? So next
Okay,
quiz
sir.
is on Wednesday, right? So maybe some 20-25 objective type question, which covers the first half of the second unit. Okay. Okay.
Okay, sir.
Yeah, each unit will be having two quizzes. Okay. Already we completed one, right?
Yes, sir.
Yes,
Yes,
sir.
right. So
First unit,
one first
yes,
unit,
sir.
one completed. One more problem I'll be giving for the first unit. I consider it as quiz. Okay. So for
Okay, sir.
second unit, first of MCQ type, we'll have it on Wednesday. Hmm?
Okay, sir.
Yeah. Okay. Yeah.